Okay, so today we're going to talk about energy, and you've done a little bit of exploring on your own, but today we're going to get kind of the nuts and bolts of what's called Ohm's law and how to use calculated energy. So I'm going to skip a couple of the slides to begin with because you've done some of the introduction, but we will be talking about current, voltage, and resistance today. We'll also be talking about series and parallel circuits. So this is a good introduction if you didn't already get kind of the nuts and bolts over the last few days. This is the nuts and bolts of what we're going to cover today. So this kind of compares energy. I think that this visual is a really good visual for you to be able to see how electricity works. We will also be doing some simulation in class as well. But when we have this, an electrical current, it's similar to a water system. So you have like the battery or the tank in this case of water. You've got the pipe going to the water source here. That pipe is going to be replaced for wire. So it's kind of like symbolic of the wire that we have within a battery system. And then you have the faucet or the switch. That would be like where you turn it off or on. And then you have the actual power source, right? So that's kind of how the battery works. It starts from the positive charge and goes to the source. And then you have your on-off switch as well. We're also going to be talking about resistors. A light is actually a resistor, but sometimes we have to build in extra resistance if the power is too much. Otherwise, we get burned out bulbs. So we'll kind of talk a little bit about that. Okay, so I'm going to get right to the heart of what we're doing today. We're going to be talking about Ohm's law and how we do calculations in order to figure out how much stress or strain can happen within a system without overloading, where you would have maybe a blackout situation or a blown circuit. So we have three different variables that we'll be talking about. We'll be talking about voltage. Okay, the voltage in. We'll be talking about current. That's what goes through the wires, the current, okay, which will be measured in amps. So we have volts, RV. Our current, when we talk about that, we use an I for current as far as our variable, but the way that we'll measure it is in amps. So we have our A. And then we have our resistance right here, R, which will have R for that one. And that is measured in ohms. It's measured in ohms, and it's that little horseshoe looking variable. So looking at this, we have one formula. Even though there are three there, we have one that I'm going to focus on. In fact, I'm going to pop over now to my notes, make myself a little bigger so that you guys can see the actual way that I've started to take notes here. So the one equation that I use is this V is equal to IR. This is volts is equal to our current times our resistance. That is V equals IR, VIR, V equals IR. I use that for every single one. Even if they're gonna ask me to solve for our current or amps, I will still use this equation, plug in volts, plug in the resistance, the ohms, and then I will solve for I that way. These extra little equations that they give here, it's literally just dividing by R to solve for our current, or dividing by here in this one, dividing by I, our current, in order to solve for our resistance. But this right here is the one equation that I'll use. I'm going to do one example with it. I'm going to do actually three examples today, one for each different thing that you have. So in this, you're going to have a lot of practice starting tomorrow on Ohm's law. And Ohm's law looks like this. It says a flashlight that uses 6-volt battery has a bulb with a resistance of, it looks like 150 ohms. I'm covered up a little bit. 150 ohms is the resistance right down here. When the flashlight is on, how much current will be drawn from the battery? So how much current do we have going through this system if we have a 6-volt battery and there's 150 ohms of resistance built in, okay? And you'll notice that the resistance is a light bulb in this case, but there are many forms of resistance. Okay, so I use the equation V equals IR every time. In this one, I have my voltage. I have a 6-volt battery is equal to I don't have my current, which is measured in amps, by the way, times I do have my resistance, 150 ohms. Well, to solve for this, numerically, I'm going to divide by 150 ohms, right? 150 ohms. And you don't have to put the actual the measurements here, but I wanted you to see them. This is going to be measured in amps. It is very important at the end, though, to make sure that you do put those. So 6 divided by 150 is 0.04. Our current is 0.04, and this is where it is important. Amps. Okay. I will be taking off if you don't have these when you do your assignment, so make sure you put what they are. So current is measured in amps, voltage is V, okay, for voltage, and then ohms, our resistance is measured in that symbol right there, which is ohms. Okay, so that's the example that I'm going to give here. You have many different examples. Sometimes you're solving for the current, sometimes for your voltage going in, sometimes for your ohms, but you can use Ohm's law in order to solve. Okay, so the next concept that we're going to be covering, there we go. So the next concept that we're going to be covering is the idea of a series circuit versus a parallel circuit. I'm going to actually pop down so you can see the difference. A series looks like this. It's a series of, you'll notice there's actually a couple of resistances built in here, but it goes around in a flow like this, whereas a parallel circuit looks like this. It has parallel lights. This is how lights actually at Christmas, lights used to be built right here in this parallel idea. So we're going to be talking about a series circuit and a parallel circuit and the similarities and differences between those two things. So I'm going to tell you that in a series circuit, the voltage total, you'll be adding all the voltages together. It's the sum of all the voltage drops in a series. Whereas in a parallel circuit, the current is going to be what adds up. The total current equals the sum of the individual branches. Okay. Okay. So I actually took it upon myself. There's this chart, but it actually has two, like it goes to 2 pages, and that's super confusing. So I'm going to have you focus instead on this. So I'm going to talk about the difference between, as far as calculations go, between a series circuit and a parallel circuit. In a series circuit, we just saw your amps, okay, your current, which are measured in amps, they actually are equal to each other. They stay the same all the way across. Whereas in a parallel, your voltage never changes, okay? Your volts never change. So that's the difference between them. So again, in a series, your currents are always going to stay the same. All the way through the entire thing, your current will never change. So when we just calculated this was a series. This was a series, it was not parallel. It is 0.04, which means it's 0.04 all the way through the system, okay? But in a parallel, that's different. Voltage stays the same. So if you put 6 volts in, it's going to stay the same all the way through it. But your current, your amps, they all add together in order to get the total amperage. Okay, whereas here, the voltage, do you see how those are inverse relationships with each other? Here, the voltage, in a series, you add up all the different volts throughout the system and it will give you the voltage total. Now, since these are opposite of each other, so is this right here. What I really have is a reciprocal idea here. You take one, so in this one, you add the total resistance in a series, you just add up all the resistances. And I'm going to show you an example of this in a second. But in parallel, on that one, you take 1 over the resistance and then you divide, and then ultimately you do 1 over that for this one. Okay, you can see those all in the PowerPoint as well. All I've done is taken these and written them this way instead because I feel like it's easier. These are the 3 different equations that we're going to use. So now we're going to see one example. We're going to see an example of this. In order to do that, I'm actually going to take out a sheet of paper separate so that I can have these to cross-reference as well. So here is our first example. We're going to do two. This one is our series example. This one is our series example. Okay, so in this series right here, the first thing I want to do is calculate the total resistance. So here I'm calculating the total resistance. So this is like my step one. I'm going to get the total resistance, RT. Well, going back to our series, that means that I'm going to add all of the resistances through the interval. So I have resistance total is equal to, well, we actually have 1, 2, 3 different resistors here. We have 3 different resistors. The first one, it looks like, is 220 ohms. So I'm going to add 220 ohms plus my second resistance is 470 ohms. And these might be lights. They might be a microwave. It might be a literal resistor, which is like a built-in let's stop the flow, or we need to tone it down, otherwise it's going to blow something. Okay, this one is a 1.2K. 1.2K. What that is 1,200. So I'm going to write it that way just because it's easier for me to not have to deal with the K's and such right here. So that is my resistance total. When I add that together, I have 1,200 plus another 220. So it looks like I'm at 1,420 plus 470. Okay, I'm at 1,900 ohms. The other way you might see that written, if you were looking at like a answer key, they might put 1.9K ohms. That's very common, so I may as well get you guys used to that concept. Okay, 1.9K thousand ohms. Okay, so I've done my total resistance. The next thing it asks for, it says to find the current. Find the current. Okay, so that's what I'm going to do. So 2, I'm going to find the current. Current is the letter I for us, and this will be measured in amps. Okay, the total current. So if I go over to here, it looks like my total current is actually equal to each one. It means my current doesn't change over the entire system. Okay, so the problem is that in this picture, they're not giving me the current. If you look, it says IT, our total, but if you look all the way around, we don't have any current through it. So I'm going to have to use Ohm's law. V equals, this is voltage total is equal to I total times R total. Remember, I always use VIR. V equals IR. Okay, so that's what I'm using here. So now we're talking about our total voltage is equal to our IT, our current total times my resistance. Well, I just got my resistance total, which is great. I actually do know my voltage total, which would be the next thing that I have to find anyways. But my voltage total going into this, we know that it's 12 volts. We know that it's 12 volts. So I have 12 volts is equal to, I don't know my current total, but I know that it's the same all the way through the system, times my resistance total, which I just got was 1,900 ohms. Well, if I want this, I'm going to divide by 1,900 ohms. 1,900 ohms. Okay, so I'm going to do the math on that. If you look, so in my calculator, I'm doing 12 divided by 1,900, and I get about 0.006. Okay, so my I total is equal to 0.0063. I'll do amps. 0.0063 amps. Okay. You also might see this as sometimes you'll see 6.3 milliamps. So I want you guys to be, and sometimes amps are AMPs as well. I usually put A, but amps is another way to put it there, AMPs. But I want you to start seeing that, because if you move this decimal 3 places, okay, you'll see milliamps sometimes as well. Okay, and in that one, that means each one of them, my current through every one, they're asking specifically like for I at resistor, the current through resistor 1, well, that's going to be 0.0063 amps. The current through resistor 2 is 0.0063 amps. And the current through resistor 3 is 0.0063 amps. This is where we know now that our amps never change. Our current for this one, our current stays the same. It's equal all the way across it. The last thing we need to find is the voltage. So in this one, the voltage at each one is going to be different, right? So here we found our total resistance. We already knew our individual resistances, so they'd ask for the total resistance. The next one, they asked for the current flowing through each one of them. So I just found the total, which means that at the individual ones, it's all that 0.063. And now it says what is the voltage across each one. So in 3, I'm having to find my voltage total, my voltage at resistor 1, my voltage at resistor 2, I should put R, and my voltage at resistor 3. Now these ones are not going to stay the same. If you look for series, they'll all add up to the total voltage. So we have the total voltage. That one's given. That is 12 volts. But we're missing these 3. Okay. But in this one, if I know Ohm's law, I know now V is equal to I times R, then I know that the voltage at 1 is equal to the current at 1, times the resistance at 1. So the voltage at 1, which is what I'm trying to solve, is equal to the current at 1, which is my 0.0063, times my resistance at 1, which is 220 amps. So I'll do that math really quick. We get 220 times 0.0063, and I get that the voltage at 1 is 1.386 volts. Now I do the same thing for 2. The voltage at 2 is the current at 2 times the resistance at 2. Well, my voltage at 2 would be that 0.0063 times my resistance at 2. Well, my resistance at 2 is 470 ohms. My voltage at 2 is equal to, again, just doing the math here, 470 times 0.0063, and I get 2.961 volts. And the last one, the voltage at 3 is equal to the current at 3 times my R, okay, my resistance at 3. My voltage at 3 is equal to my 0.0063 amps times my resistance is that 1200 ohms. So I do, again, 0.0063 times 1200 ohms, and I get 7.56. 7.56 volts. Okay. So the last thing I wanted to check is to make sure that when I add all these together, I get about 12 volts. Because my voltage total should be these all added together. And we already know that the voltage total is 12 volts going into it, but I want to double check it. So I have 1.386 plus 2.961 plus 7.56. So all the voltage totals over the system should be that 12 volt. So I'm going to double check it just to make sure that I've done my math correctly. So I have the 7.56 plus 2.961 plus 1.386, and I should be at about 12, and I am. This would be a rounding issue. So as long as I'm very close, it's probably just a rounding. And I got 11.91, which would be close enough to that 12 volts. Okay, so that is my series example, and you can see that they take quite a bit of time, and that's why you guys are only going to practice probably 1 or 2 of these a day. So there's one more with the parallel. There's one more example with the parallel. I will let you guys follow this one, but you're doing pretty much the same thing I just did, except you're using different equations. These are obviously flipped. Okay, the concept is flipped where your voltage, so now your current is what you're adding, your voltage is what's staying the same, and your resistance is the reciprocal. It's the idea that it's the reciprocal, so you have to do a little bit more calculation. You'll notice that I have attached my work here for you guys to look at for this one. To calculate your total voltage throughout a parallel. But it's very much the same thing. You're just using equations. So you use what you have, and you're using Ohm's law. You'll notice right away, here's Ohm's law again. So you'll be using Ohm's law throughout the example. Okay, so go ahead and finish taking notes on this parallel circuit. Take notes on that, and you'll be done for today. And then we'll get into examples next week. Have a great Monday.